All right. So we're going to talk now about isomers a little bit. And isomers are really compounds that have the same formula, but a lot of times they have different connectivity. And based on the different sort of connectivity that they have, it will give them some different types of properties. We're going to talk about a few different types of isomers. There are structural isomers, which are sometimes referred to as coordination isomers or linkage isomers. There's also stereoisomers, which have the same bonds, but different sort of orientation in three-dimensional space. And those can be cis or trans isomers, or what are sometimes referred to as optical isomers. We're going to go through each of these here as we go through it. So the first type of isomer is what's known as a coordination isomer. And the difference is really in what is acting as the counterion and what is acting as a ligand that's attached. So if we look at the first one here, this is our complex ion. And in the first one here, we have a chromium in the middle, and we have 5 ammonias. And here the sulfate is actually attached there to it. And working outside of that is our bromide as really a counterion. Now, although if we count up everybody that's there, we have 1 chromium in each, 5 NH3s, 1 Br in each, and a sulfate in each. They have exactly the same elements present, but in the second sort of coordination compound, we have our chromium in the middle with our NH3. The difference here is in this particular guy, it is the bromine that's going to be attached here as a ligand. And the sulfate in this case is actually acting as our counterion. So in terms of coordination isomers, again, they do have basically the same sort of formulas in a sense. They do have the same stuff present, but the difference is in one case, the ligands are different in terms of how they're attached. And again, obviously here the sulfate is directly attached to the metal, while the bromine is directly attached in the second one. That is going to give them some different properties, as you can just see just in general. It also will give it a different sort of charge as well, depending on what ligands are attached there versus it being a counterion. Now, a linkage isomer is when a ligand has the ability to sort of attach via different sort of elements. Not that it will attach with both elements at once, but here, in this case, if we look at NO2 minus, which is a monodentate ligand, in the first case, it is the nitrogen that is attaching to the metal. While here in the second case, it is still the nitrite that is our ligand, but it's actually going to attach via the oxygen here. So here in this case of a linkage isomer, we do have basically the same ligand involved. It is still attached to the metal, but the attachment point in that ligand is different. In one case, it's the nitrogen using its non-bonding electrons, and in the other case, it is the oxygen, which gives us linkage isomers. How they are basically linked to the metal is different in this particular case. Any question on those two types of isomers there? Now, let's talk a little bit about stereoisomers. Stereoisomers give rise to sometimes cis or trans isomers, and cis or trans isomers we'll talk maybe a little bit about in organic, but you see a lot in organic, and cis means really the same side, and trans means opposite sides. And when we talk about sort of organic chemistry, a lot of times we talk about a double bond and whether or not something is sort of on the same side of the double bond, or they're on sort of opposite sides of the double bond. And in the case of this type of situation, we're talking about sort of the plane of the molecule. Are they on the same side or opposite sides? So these are the same atoms that have the same bonds, but they will have different bond angles depending on where the groups are attached. These are common in square planar complexes. Perhaps you remember square planar, exception to the octet rule, expanded octet. A little something like that action makes a square in a plane, right? With some non-bonding electrons, 6 electron pairs, 4 bonds, yeah, something like that. And again, what we're looking at here is sort of above or below the plane of the molecule, is sort of what we're talking about when we talk about sort of cis or trans in this particular case. And here in this case, we can look and we can see in the first one we have cis, and these guys are on basically the same side of the plane here of our molecule, complex ion. And on the second one, this is trans, and they are on opposite sides. If you want to look at the chlorides, you could also look at the ammonias as well. They are opposite sides. So we got trans and cis, again, same side and opposite sides. As you can see, there's a slight difference in even the coloring here. They both have identical sort of formulas, but one's a more darker yellow, one's more of a pale yellow. And the only difference in the formulas is a lot of times people write trans or cis sort of in front of the formula to indicate where those groups are sort of positioned, either on sort of on the same side or the opposite side of the plane there in that particular case. And here is our trans and cis, and this is more of an octahedral arrangement. And I think I drew octahedral earlier, but square planar is obviously what we just saw there previously. This is our octahedral here, and here we could look at the chlorines, and this being sort of the plane of the molecule there, and the chlorines here in this particular case, one's above and below the plane of the molecule, and that's sort of opposite of each other, and that will give us our trans, as opposed to here where essentially our chlorines are really on the same sort of side here of the plane of the molecule, and that will give us our cis location. Once again, they're both the exact same formula. They both have the exact same coordination numbers of 6 in this case, as opposed to our square planar here where coordination number would be 4 in this particular case, right? Now, optical isomers are isomers that have opposite effect on plane polarized light, and molecules that have a non-superimposable mirror images. These are what are referred to as being chiral, and these type of isomers are sometimes referred to as being enantiomers. So a chiral molecule means that essentially if you take a molecule and you put it up against a mirror and you take the reflection that you see and you pull out the reflection from the mirror, you would not be able to superimpose those molecules exactly on top of each other. So the classic example of sort of visualizing chiral is your hand. You take your hand like this and put it up to the mirror, you get your other hand as the image is coming out. If you pull out your mirror image, you can do whatever you want to that mirror image. You can rotate it, move it around. You'll never be able to get it to sit perfectly on top of the original one. So even though I got palms down on both of these, my thumbs are on the wrong side, right? If I get my thumbs on the right side, I got palm up and palm down. So that's not going to sit perfectly. So when you have a chiral molecule, one is up against a mirror, and if you pull out that mirror image, even with sufficient rotation, you will not be able to get it to sit perfectly on top of the original sort of compound. There will always be a compound that is basically off in terms of the geometry of it and its location. Achiral, which is something you sometimes talk about as well, these are guys that have mirror images that will superimpose. So if you have something that's considered an achiral molecule, you put it in the mirror image and you pull out that mirror image, you can rotate it in a way that it will fit perfectly on top of the original sort of guy. And when we look at sort of polarized light, we have sort of guys going in two sort of directions. And there's our hands there. And again, our hand is again, a mirror image that will not superimpose. There's always going to be something that is not going to fit right. Again, thumbs on the correct side, but palm up, palm down, not going to fit correctly here. So if we look at this one here, and this is a mirror images, the image of 1 and 2 are identical. is identical to 2 that cannot be superimposed, and there's no way to do that. So it may be hard to see, but if we take our original sort of guy that's right here, and we again reflect it into the mirror, we'll get these guys. And what actually happens in terms of the reflection is when this guy comes, he's actually going to be reflected in the back. And what that's going to create in the mirror image is this different bond, in a sense, that you do not have in the original one. So when you pull out that sort of mirror image, that bond is always going to be in sort of the wrong location, even if you try to rearrange it. And these guys will not superimpose on each other because now the bottom nitrogen is actually hooked up to the back nitrogen in the mirror image, which is different than the original guy. So that is where it's not going to be able to sit perfectly on top of each other when we look at these two sort of structures. So this would be a chiral compound where that mirror image does not superimpose on top of each other. Now, if we look at this here, the trans one and his mirror images are identical to each other, so they are superimposable. And if we look at the first one here, which is our trans, when this gets reflected, this guy basically gets reflected, and this guy gets reflected to the back. We end up with really the exact same connections that we originally started with, if we look at sort of the connections here. And we have these exact same connections. So when we pull this guy out, we will have no problem basically dropping it right on top of that guy because we have the same connections. Again, if we look at our cis isomer here, we're going to get, once again, this guy reflecting to the back, and that's going to create that bond like we saw in the first one. That is different than that kind of closer bond that we have here. And again, that's going to create a different bond angle as how it's hooked up. And as you rotate, that's always just going to be slightly off and not going to be able to, again, superimpose on each other. And these guys are mirror images that will not superimpose. They're chiral, and they would be considered optical isomers. They will basically move plane polarized light. You actually measure how far it moves it, the angle, which we're not going to get too far into. Any question on that? So sometimes it's very hard to visualize these things. Sometimes building models is really easier to kind of see it. It's just those slight little connections between an atom and an atom that gets moved in the mirror image because it gets sent back, that when you do pull it out, it will not basically correspond. So enantiomers, as I mentioned, are two mirror images where they're non-superimposable. A lot of biomolecules are chiral, and a lot of drugs are also chiral, where only one of the isomers are effective, again, because of some of the different connectivity that you get. You will get some different properties that will occur. All right, so that's a little bit about isomers. We're now going to talk about, in this part of it, the bonding that occurs within a complex ion, and more specifically, what happens with the transition metal and its d electrons, and what happens in terms of how they are sort of distributed in a complex ion. So if you remember when we talked about the formation of hybrid orbitals, right? Hybrid orbitals like sp, right? sp2, sp3, a little sp3d, sp3d2 perhaps, yes, I hope. The Vesper model doesn't work very well for complex ions, but there is sort of a relationship, as we've been talking about, again, as more of a Lewis acid base relationship, and where the metal ions accepting these its d orbitals or electrons into its d orbitals. The hybrid orbitals used by metals does depend on the number of ligands that are present. As you may remember as well, this is typically for linear arrangement, right? That is your trigonal planar. That's your tetrahedral. That's your trigonal bipyramidal. And that is your octahedral, right? Arrangement sort of deal. And when we look at this, this is sort of what we envision. the ammonia bringing its non-bonding electrons in to those d orbitals of the transition metal that's there, where it has room to accept those electrons, again, to sort of make those bonds that's going to happen. So there's a few different sort of geometries that we associate with complex ions. There is the tetrahedral arrangement, and tetrahedral is sp3, and that is your 109.5 degrees, right? We also have our square planar, which is our sp3d. That is our 5 electron pairs, basically, and our bonds there. And we have our linear, which is sp, right? Which is a straight line there. Now, there are very common sort of structures that sort of go with coordination numbers. So typically speaking, somebody with a coordination number of 2 will basically do this more linear geometry. Somebody with a coordination number of 4 will go tetrahedral, r square planar. Again, tetrahedral has 4 spots, and square planar has basically place for 4 bonds to occur. And 6 coordination number is typically the octahedral arrangement, which looks like this here. And again, with 4, it could either do a square planar or a tetrahedral sort of arrangement. So let's talk a little bit about our d orbitals and our d electrons for our transition metals. In the absence of any ligand being present, all 5 of those d orbitals will basically be on the exact same energy level. They'll all be equal to each other. And as you should know, right, electrons go into orbitals, especially subshells where there's multiple orbitals. They go in one at a time, right? And then they come back and pair up, right? So that is how electrons go in there. That's Hund's rule. Maximal stability is maximizing the parallel spin that occurs. Electrons go into the atom, right? Lowest energy level, then to the next lowest, then to the next sort of lowest. When we do start to get ligands attached to our transition metal, there is actually a splitting that occurs in the d orbitals of the transition metal. So when we look at this splitting, and by the way, this is for a coordination number of 6. This is octahedral we're looking at here in terms of the splitting. We will see that the dxy, yz, and xz here are going to go lower in energy, and these 2 d orbitals will go higher in energy. The difference in energy between the lower d orbitals and the higher d orbitals, that is what is sometimes referred to as crystal field splitting. It is sometimes abbreviated with a delta symbol. It is also the same formula that you use to calculate energy, equals h times the frequency, or maybe you remember what speed of light is the wavelength times the frequency, which gives us E is equal to hc over the wavelength, right? C is the speed of light. Frequency, and obviously wavelength is in meters in this case, right? So what is the importance of this? The importance of this is basically how the electrons will populate these d orbitals. So for example, if the electrons go in, they would definitely go into the lower energy level first. And at this point, what's going to happen is they're going to kind of look at the crystal field splitting here and the energy difference between the lower energy level d orbitals and the higher energy level d orbitals. And what's going to happen is if it's a case where that energy splitting of those lower d orbitals and the higher d orbitals is a pretty big difference in terms of the energy, what's going to happen is those electrons are going to decide, no, thank you, I will stay down here first, and I will fill up these electrons down here. And then if I necessarily need to, I will then go up to the high one. Now, if we look at the splitting between the lower d orbitals and the higher d orbitals, and they see it's not that big of a difference between them. The electrons will populate the orbitals like normal. They'll just go up there and then come back and start filling up. Now, depending on how big or small this crystal field splitting is, will give us a really different type of complex ion. It will give us some different properties for these metals, because in the case on the left where we have a really big difference in the energy, we have a lot more paired electrons, right? As opposed to on the right, we have a lot more unpaired electrons, right? Which is sometimes referred to as being paramagnetic, means more unpaired electrons. So these give rise to different types of complex ions, which are sometimes referred to as high spin or low spin type of complex ions based on the number of unpaired electrons that are present. So again, in this situation, we could calculate the actual energy by using that equation that we talked about there. And again, that is the same as hc over the wavelength. By the way, when we do an absorbance reading, as we know, we always want to pick the maximum absorbance, right? And the wavelength at the maximum absorbance. That way, all of our measurements will be taken. If we chose a wavelength over here, we would only have about that much of measurement ability, as opposed to over here where we obviously can get a lot more. That is what you did in your experiments, right? When it gave you that first rainbow type color thing graph, where it gave you the little graph that went up and you're supposed to pick the wavelength and lock in the wavelength. And that's basically what you were doing. You're picking the maximum wavelength for absorbance so that all your values will hopefully be on the scale. So if we wanted to see sort of how this works, and I think it's filled in for you, so we'll just talk about the calculation here. The absorbance maximum for a complex ion occurs at 470. What is the color of the complex, and what is the crystal field splitting in kilojoules per mole? So one thing that you may know, or maybe if you don't know, is that the color, for example, the solution that we see is complementary to the color of light that's being absorbed. So if our solution looks red, like we had when we did like the iron experiment, we do not set our wavelength to red's wavelength, but we actually set it to the complementary color to red, which if we look on our color wheel would be over here. So you would set your wavelength somewhere in this region, and that will give you your maximum absorbance. So in this particular case, if our guy has his maximum absorbance around 470, which would be right about here. If we have our maximum absorbance at 470, it will appear orange to us, the color of the solution, as that is our complementary color. So again, we always see sort of the complementary color to the light that's being absorbed. So in this case, we can figure out the energy by using our energy equation, which is our E is equal to h times the frequency. In this case, we do have the wavelength. So we will take h here and c, those are both constants. That's Planck's constant, 6.63 times 10 to the minus 34. That is Planck's constant, which is a constant. And obviously c is our speed of light. When we use this equation, because this is in meters, we do have to convert our nanometers into meters. And nano is 10 to the minus 9, right? So 1 nanometer is 10 to the minus 9 meters. So we have to do that conversion. When we do that, that gives us 4.23 times 10 to the minus 19 joules per atom, basically. And now we can use Avogadro's number here and multiply it by Avogadro's number, and the atoms will cancel, and that'll give us something like 255 kilojoules per mole. So we're basically taking this times Avogadro's number per mole. Those guys will cancel. Any question on that calculation? So very similar to probably something we've done previously. And again, this is the way we could calculate the crystal field splitting if we know basically the maximum absorbance of our complex ion. Any questions on that calculation there? So let's talk about how do we know if we're going to get sort of a big difference in these d orbitals or sort of a small difference in these d orbitals. So it does depend on the ligands that are present. And this is basically a spectrochemical series. These are what are considered weak field ligands. These are considered strong field ligands, which means if these guys are present on the left-hand side, we will get a small difference in a weak field. And that means that our electrons will fill basically one at a time, and we'll have a lot more unpaired electrons. This will give rise to what is referred to as a high spin complex, because you have a lot more unpaired electrons. Now, if we have somebody that is over here, we will get a much larger splitting that's occurring. And in this particular case, what's going to happen is we're going to get a lot more paired electrons. So less unpaired electrons in this large, strong field. And this will be a low spin complex. Now, guys, sort of in the middle, it does depend. You could kind of do it both ways. And sometimes they will tell you in a problem, do it for like the high spin or do it for the low spin. And there are certain situations where they may not tell you which way to do it. And that's because it doesn't matter. It will come out the same regardless of which way you do it, because there's only so many electrons to be distributed. So sometimes they may not give you any information. Usually that means that you kind of do it either way, because the number of electrons there will come out the same regardless of which way you do it. And in other situations, they'll sort of tell you which way you need to do it. So let's take a look at one and sort of what we're sort of talking about here. Let's take a look at the nickel complex here. And when we look at this nickel complex, first off, we know the coordination number here is 6, which means we are going to get the octahedral splitting, which is sort of what we've been looking at in those pictures. So the first thing we want to figure out is what is the charge on our nickel. So we know that Br is -1, and that is a -6. That's a -2 overall, which means my nickel in this case has a +4 charge. So if we look at the periodic table in this particular case, nickel is number 28, which means if we write the electron configuration for nickel, that is argon 4s2 3d8. So nickel with a +4 charge, which means it has 24 electrons. So if you remember at the beginning of this chapter, we talked about when transition metals lose electrons, they will lose the s electrons first, then they will lose electrons out of the d, and that means that we will end up with argon 3d6. So this is important because these are the 6 d electrons that we want to distribute in our little picture here for our crystal field splitting. So first off, any questions on that there? All right, so we know it's octahedral, so we know we're going to get this splitting. The other thing we want to look at is the ligand that is there, which is Br. And when we look at Br, it definitely is on the weak field side. So that means that when we get this splitting that occurs, we're actually going to get a weak field, which means when we go to distribute these electrons, we will go 1, 2, 3. And because this is weak field, they will go up here and then come back and pair off. And in this particular case, we will end up with a very common question, which is how many unpaired electrons? And in this case, we do have 4 unpaired electrons. This would also be considered a high spin complex because of all the unpaired electrons that are present. Any questions on that there? And again, obviously, this is our X, Y, Y, Z, and all that guys, and our square guys up here. Any questions on that there? All right, so why don't you try the three that are remaining? Why don't you draw the crystal field splitting? And why don't you also, how many unpaired electrons in each of these? Nickel obviously is 28 and iron is 26. Yeah. So take a few moments, draw those guys for each of those and see what you come up with. Okay, so let's take a look, see how you're doing. We'll just roll down to the one below it first. So when we look at our nickel here, again, this is 0, which means it is going to be +4 in this case, which will give us the same 6 electrons as we had previously. By the way, the coordination number here is also 6. Again, that is bidentate, so that's 2 times that. And that again gives us our octahedral splitting. So we will get either the splitting on the left or the splitting on the right. We do want to look at the ligand that's there, and that is our ethylenediamine. Looks more like a strong field splitting. That means that we're going to get a bigger separation between the lower d orbitals and the higher d orbitals. So now when we go to spread or distribute our 6 electrons, they're going to decide after that third one, that is way too high to go up. We rather just kind of pair up down here, and that's going to lead us to 0 in terms of our unpaired electrons, right? In this particular case. This would also give us a low spin complex, as obviously we have a lot more paired electrons than unpaired electrons. Any questions on that one there? All right, then let's take a look at our iron. So our iron complex, iron with no charge, is argon 4s2 3d6. Again, electron configuration from the periodic table. Here we'll go with the top guy, which is our fluoride. And in this case, if we look at it, that's -1, -6. That's a +3 in this situation. And that means that we will end up with an iron with a +3, which is 23. Going to take out our s electrons and one of the d, and that will leave us argon 3d5. Those are the 5 electrons we need to distribute here in our picture. Here they did say do high spin. So high spin usually results from a weak field. So we will do our weak field here and distribute our 5 electrons. 1, 2, 3, 4, and 5 in this case. And that would obviously give us 5 unpaired electrons. And definitely would give us a high spin complex, as we have a lot of unpaired electrons in this particular case. Any questions on that there? Now, if this happened to have been, say, a low spin complex, you will end up with something that looks like this in this case, right? And that would mean that we would have a much stronger field, and you would end up with actually only 1 unpaired electron if they wanted, say, the low spin. So sometimes those guys, again, in the middle, they will kind of tell you to do it one way or the other. They'll give you some indication. But here you can see, depending on what's happening, you would have different unpaired electrons. Any questions on those there? Yeah. Yeah, in a lot of cases, those ones kind of in the middle, they'll kind of tell you. Again, if they don't really tell you, a lot of times what that means is, like I said earlier, based on the number of electrons you have, it won't make a difference. So, for example, if you had something that only had 3 electrons, right? It doesn't matter if it's high spin or low, or large field or strong field or short field, because you only have 3 to put in there. They're going to go on the bottom, right? Regardless, so it won't make a difference. So there is some situations where that does occur and you don't get that information. Usually, if it's not sort of on the outside ones, for sure, one way or the other, they'll kind of give you some indication. Like I said, they'll either say high spin or low spin, or do it as strong field or do it as weak field, and they'll kind of give you that information as to how to do it. Other questions? You should probably know this little series, at least the end ones, for sure. Yeah. Let's take a look at the last one, which is the same iron here. And in this case, we have -1, -6, -3, still the +3 in this case. So we're still going to end up with our 5 electrons like we had previously. Now we just need to decide based on the ligand that's there, which is CN, and that definitely is more of a strong fill or large separation. That means we would come down here, and we actually would end up with this arrangement here, as we would go 1, 2, 3, too big, 4, and 5, ending up with 1 unpaired electron in that case, which would be low spin. Any questions on that? So what we're looking at specifically here is, just so we understand, these are complex ions that have a coordination number of 4 and an octahedral geometry. So that is the splitting that occurs with a coordination number of 6. Did I say 4? I'm sorry. Coordination number of 6 and a octahedral splitting or geometry that's happening here. Now, it is different when we look at some other sort of geometries, and we'll take a look at it in just a second. But here again is our high spin, low spin. And again, in the high spin, we have a much weaker field, and that's going to lead to a lot more paramagnetism, unpaired electrons, as opposed to strong field, where we get a greater separation happening, and electrons will rather pair up lower in energy than higher. Here's all your different combinations that you can have, from basically 6, 5, 4, 3 sort of electrons. And again, here on the left, these are all high spins, small separation. On the right, these are all strong field, higher separation, a lot more unpaired electrons. Now, let's talk about what happens when we have the tetrahedral geometry. The tetrahedral geometry comes with a coordination number of 4. So this is a coordination number of 4. It is basically just like the octahedral splitting, except they just flipped the other way around. So the 3 are up on top and the 2 are on the bottom. It works the same way. In this case, electrons would fill lower and then decide, is this difference too big or too small? And if it's not too large, they will continue to feel like normal, and vice versa. Obviously, if it's a larger strong field, we'll get more paired up electrons. So coordination number 4 with the tetrahedral geometry will have this type of splitting that occurs. Now, square planar, which is also coordination number 4, gets a little craziness happening here in terms of the splitting. So we do feel like normal, again, lowest energy to highest. You will not be responsible for square planar because it just looks scary. But it does work basically the same way. You just kind of feel lowest to highest. So you are responsible for tetrahedral coordination number 4. This splitting, which is basically the opposite of octahedral coordination number of 6. So you're responsible for octahedral and square planar, or tetrahedral, I'm sorry, tetrahedral geometry. Any questions on that there? All right, that wraps up this chapter here. Off here to chapter 21, which is nuclear chemistry. And nuclear chemistry involves obviously radioactivity. And radioactive nuclei, they will spontaneously decompose into smaller nuclei through radioactive decay. And when we have something that goes through sort of radioactive decay, it is obviously unstable. And it usually involves decomposition or decomposing the nuclide. When we talk about sort of the nuclide, that is sort of, the atom or the isotope that we're talking about. It usually will involve some type of emitting of particles, and also times a lot of energy is given off in these sort of processes. When we talk about the nuclei that undergo sort of the radioactive decay, that is what is referred to as the parent nuclide. It will then make the daughter nuclide as it goes through that sort of decay process. Um, a lot of times it will continue this process until it sort of hits something that's a little bit more stable. And we'll talk about some ways that we can look at stability in this chapter. If you look on the periodic table, which usually brings you to sort of the bottom row, the very, very bottom row, anything above 84 in terms of its protons are typically radioactive. A lot of those on the bottom of the periodic table is where we have a lot of those sort of man-made elements, and that's made by sort of, bombarding stable nucleuses with particles, makes it unstable and makes some of these man-made things that have, like, nobelium and einsteinium and all those type of names. Now, when we talk about radioactivity, there's a few different types of radioactivity and particles that we see in nuclear chemistry. We remember our friend Rutherford. He did something. What did he do? He did a gold foil experiment. That's pretty good. And he shot alpha particles during this gold foil experiment. And alpha particles are alpha rays. They are oftentimes sort of symbolized a couple of different ways in nuclear chemistry. A lot of times they will use the alpha symbol and a 4 and a 2. Or it really is like the helium nucleus. So very commonly as well for an alpha particle, they'll sort of use the helium symbol to represent that. By the way, the number on top is it is the mass number, right? Number on the bottom is the atomic number. Yeah. Good talk. Atomic number is the number of protons. Just protons, right? Yeah. We can find that on the periodic table. Yeah. That is the number above the symbol, right? Is the atomic number. Mass number is the number of protons and neutrons, right? Do we find the mass number on the periodic table? Is it the number on the bottom? No, it's not the number on the bottom. Yes. In case you missed that, let me do it on a happy face one more time. Yes, that is the atomic mass. Yes. The mass number is really the number of protons and neutrons. When you calculate the mass number, atomic number, number of protons, neutrons, and electrons, they all should be positive whole numbers. Good way to remember that. If you look on the periodic table, pretty much none of those, the bottom numbers or whole numbers, are all decimal type numbers. So that is the atomic mass. What confuses people a lot of times that number is very close to some mass numbers that you come across for isotopes, right? Isotopes are the same element, but they have a different mass, right? And they have different mass because they have different numbers of neutrons, right? When we talk about the beta particles, beta is symbolized with the beta symbol. It is also an electron, so sometimes people will just use an E to represent that as well, are the beta symbol. It basically has a -1 charge like an electron. Gamma rays, if you remember gamma rays on the electromagnetic spectrum, it was all the way at the very end, usually, past X-rays with really short wavelength, right? Short wavelength means high energy, right? So very high energy, pure energy. It is usually abbreviated with the gamma symbol, the 0, action happening there. There's some other symbols, as we will see as we go through this chapter. Sometimes it will emit a positron, which is an electron with a better attitude. Thank you very much for not laughing. There you go. Uses the same symbols as a beta particle. So those are the symbols that we use there. Now, since they do use the same symbols, there's usually some type of indication to let you know that they're talking about either the beta particle or the positron. I would say 9 times out of 10, even higher probably, if you just see a beta symbol, it probably is a beta particle, the negative version of it. A lot of times they may do something like that if it's a positron and put the positive sign there, or obviously put the numbers there on the left. So I would say if you just see sort of a beta symbol by itself, nothing else written, it's probably safe to assume it's a beta particle. Again, usually they'll sort of indicate the positive part of it to let you know that it is sort of a positive or positron in this case. There are certain reactions that basically undergo what is referred to as an electron capture, and that is pretty much what it sounds like. It is something gaining an electron on the reactant side of the arrow. Now, speaking of sort of equations and sides of arrows, when we talk about something that goes through a decay process through some type of emission or something like that, that means the particle will end up on the product side. If you see something like we see here, like an electron capture, that particle is on the reactant side. If you have bombarded something with like a neutron, means you basically shot a neutron on it, it will be on the reactant side. So anything like electron capture, or you bombarded something with a particle, those particles end up on the reactant side. Anything that goes through some type of decay where something is emitted or it goes through an emission, those particles end up on the product side of the arrow when we sort of write equations. Any questions on that there? So as we just talked about there, top number, mass number, bottom number, atomic number. And again, remember that the atomic number definition is the number of protons, not the number of electrons. So that is not really the definition, it's just the number of protons. In a neutral, it will tell you the number of electrons as well. Out of those two, the mass number and the atomic number, the one that's most important in terms of what element you're dealing with is the atomic number, right? So if you look at the periodic table, every element has its own atomic number. No element repeats numbers up on top. And that means that if you know the atomic number, or you know the number of protons, which is essentially the same thing, you will know what element you're talking about. So that's a really good thing. Periodic table and understanding that's really, really important. Some other symbols that we might come across as well. A proton is sometimes abbreviated with P, 1 and 1, or a hydrogen. A neutron, like I wrote a second ago, is also there. And then again, there's some of our other very common symbols. It's really good to know the symbols, and more importantly, the charges that go with the symbols, as it's kind of helpful when you're writing sort of equations. Any questions on that there? Okay. By the way, if I do write a isotope like this number is which number? Copper 64. 64 would be the mass number, yeah? Because we know if we go to the periodic table and look up copper, we can see above it, it says 29, and that would be our atomic number, right? So that is also a very common way that isotopes are written, sort of the symbol dash a number, and that number is the mass number typically. Now, when things go through radioactive decay, they oftentimes will emit these particles in the process. And depending on the type of radioactive decay, you may need different types of protection, if you will. So for example, these are pieces of lead, and you can see alpha particles only go about 0.01 millimeters into lead. So that would be enough if it was sort of an alpha emitter. But if you had a beta emitter, you would need a little thicker piece there of lead. And clearly, if you need a gamma emitter, you need a lot more protection. As we'll talk about a little bit towards the end of the chapter, some things only require maybe gloves and coats and stuff like that as sort of protection. Other things you need like lead and concrete and a good amount of safety depending on the type of emitter. I will say if you ever find yourself working with radioactive materials, which you might in labs, it's always a good idea to understand what type of emitter it is so that you can protect yourself properly. If it's a gamma emitter, you definitely don't want to be standing near it all day while it's doing its thing. Here's a few different ways, again, that the symbols are represented. And like I said before, if it's kind of just bare symbol there, they definitely will put the minus or the plus, or definitely the plus in the case of a positron. So let's talk a little bit about balancing nuclear equations, which is super hard. Not really, you just need to add. It's not too hard at all. But one of the main difference, if you're not aware of what is happening in a nuclear reaction versus a regular chemical reaction, is the idea of, in a chemical reaction, like we typically do here, the only things involved are electrons, right? And bonds, right? We break all the bonds on the reactant side. They then recombine on the product side and make new bonds. So we make bonds and break bonds, and that is all about electrons. In a nuclear reaction, it is all about what is inside the nucleus, which is our protons and neutrons. And we change protons to neutrons, neutrons to protons. We screw around with what's inside the nucleus. The result of that is we do not get the conservation of elements like we do in a normal chemical reaction. Because in a normal chemical reaction, we're only playing with electrons. We don't touch the nucleus. We don't touch the protons. So if you have a carbon to start with, you will end with a carbon because we didn't play with the protons there. But in a nuclear reaction, it's all about playing with everything in the nucleus, and you get new elements that are formed. So when we balance nuclear equations, it's a little bit different than how we balance normal chemical equations. The first thing that you want to do is make sure that when you look on the left-hand side of the arrow and the right-hand side of the arrow, that all of the mass numbers equal each other. So the mass numbers on the left, when you add them up, and all the mass numbers on the right will equal each other. So if we come over here, we have 235 and 1, that's a 236. Here we have a 138 and 96 and 2. You would multiply the 2 here. So that gives us a 138 plus a 96 plus a 2, gives us a 236. So the mass numbers on both sides of the equation are balanced. The other way that we balance the equation is through the atomic number, and we want to make sure it's the same on both sides. So we got 92 there, 55 and 37 and 0 gives us a 92 there, and our atomic number is balanced. So for example, if we had this equation and say a problem, and let's just say we want to figure out, what was missing here, I would start with the atomic number, because the atomic number is going to help you determine what element's missing. So you would go to the left-hand side and go, I got 92. Right-hand side, I got 55. So if you take 92 minus 55, you will end up there with your 37. You go to the periodic table and you would find number 37. And as you would see there, that's going to be your RB. And that would be how we get our missing guy. Now for the mass number, you would do the same thing. You would have 236 on the left. On the right, you would have 138 and 2, which is 140. And that would leave you what we got there, 96 left over. And again, you would now have your sort of missing element. So this is one way that you have to balance equations. You're given everything, but something's missing. You want to attack the atomic number first in the periodic table. That will allow you to know the element, and then you can get the mass number. A reminder as well that something missing could be a particle. So if you kind of do the atomic number, it's like 0. It might be like a neutron or something like that. Or if you get a negative number, maybe it's a beta particle. So it could be like a particle missing, but most of the time it probably will be an element. Another way, like I said before, is if you have something that's an emitter, you would have, say, an alpha emitter would have an alpha particle on the other side. You would know what you started with. Again, you could figure out what will be produced on the right-hand side by looking at the atomic number and then the mass number. So if we take a look at this one here, we want to write out the equation here for the alpha decay, PO212, and we want to write the balanced equation. So the first thing is we know that we have PO and we have 212. We could go to the periodic table and we could find our PO. And if we look on the periodic table, that is 84 there. And if you look at it, that means that is our missing atomic number that we could get. It goes through alpha emission. Emission means that the alpha particle will be on the product side. So that's going to be a 4,2. If you want to use the alpha symbol, you can. If you want to use the helium symbol, you can as well. So whichever way you want to do it. So now we have pretty much most of our equations set up. We could attack the atomic number. So I have 84 on the left. I have 2 on the right. Means that my missing atomic number is 82. I once again could go to the periodic table and find 82, which you will see lead is there at number 82. And now I could do my mass number. I have 212 on the left minus 4. That's a 208, I believe. And now we would have our balanced equation in this case. Mass number on the left, 212. Mass number on the right, 212. Atomic number on the left, 84. Atomic number on the right, 84. Any questions on that one? So not too bad. Again, periodic table, probably your friend when you're doing these. And again, go atomic number first and then mass number after that. All right. So as I mentioned earlier there, again, a major difference between chemical processes and nuclear processes is really what's involved. Again, all about electrons and chemical reactions, and nuclear reactions, it's all about what's in the nucleus. That is also why in a nuclear reaction, you get a tremendous amount of more energy being given off, because in order to kind of change those protons and neutrons, you have to get into the nucleus, which requires a lot of energy. And there's a big energy sort of component to that process, as opposed to just trying to rip off, for example, our valence electrons and breaking apart our valence electrons in the outermost spot. So in comparison, as we will see, if you take like your most exothermic chemical reaction, it's nowhere near the output of, say, like a fission reaction or a nuclear reaction in terms of energy that's given off. So what's actually happening as we go through these processes, and how do we get these particles to get emitted? We could go through this, and we're not going to worry about the neutrino, which is this guy here, so we won't worry about him. He's got pretty much no mass or anything like that. But what happens in this case, for example, when we do a beta decay, because beta is -1, we actually do increase the atomic number by 1. And that gives us 7, and -1 gives us 6 on the right and 6 on the left. Same thing here, -1 and 20 is 19, matches here. So what is actually happening in this case? In this particular case, we're actually changing a neutron into a proton. So we're changing a neutron into a proton. And the result of that is, the byproduct is, it will give off this beta particle as a result of that transformation that occurs from the neutron to the proton in this particular case. Now, the mass number doesn't change, but it really does change. So overall, it doesn't change, but there actually is change happening here. So just to demonstrate that, for example, we start with 14 and 6. And because this is a neutron that's going to be converted to a proton, when we lose the neutron, we will actually lose 1 from the mass number up on top. And that will become like 13 and 6. But we will then gain a proton, which means we will gain 1 to the mass number, and we will gain 1 to the atomic number, and we will end up with 7, 14, and nitrogen. So overall, the mass number doesn't change, because we're ultimately swapping a proton for a neutron, our neutron for a proton. And basically, that's the same because the mass number is protons and neutrons. So overall, it doesn't change, but there is a change in sort of the amount of protons and neutrons that's happening there. But we got an even exchange that's sort of happening there. When we have a positron emission, what's happening is we're taking a proton and we're actually converting it into a neutron in this particular case. The result of that is a positron particle will be emitted. And the same idea here, we're just going to drop a number down. So 18 and 1 is 19. So we will basically drop down one number here. In terms of the mass number, it stays the same, but it really does change as well. So if we look at that guy there, 11 and 6 in this particular case, we are going to lose a proton, which means we'll lose one from the top and bottom, which brings us to 10 and 5. We then will gain a neutron, and that goes one more back up into the mass number, which gets us to 11 and 5 and gets us to our boron there. So once again, overall, the mass number doesn't change, but here we are swapping a proton for a neutron in this particular example. Any questions on that there? Now, in electron capture, we're actually capturing an electron. And in that process, what's occurring is a proton and an electron will combine to basically make a neutron in this particular case. And once again, here we're going to end up with really no change in the mass number because we are creating a neutron. So again, if we look at the mass number here, we're going to basically lose a proton, and then we're going to gain a neutron. So we'll add one there, and that's going to take us back to 37 and 17 in terms of chlorine as to what's going to be made in this particular case. So again, sometimes we don't really change the mass number, even though we really are. It just ends up at the same number. Probably the biggest sort of change that occurs is our alpha decay, and that's going to change the mass number by 4 and the atomic number by 2. Now, fission is the process where a unstable nucleus will break apart into 2 new nucleuses and give off some neutrons, and a lot of times it will involve energy as well. Now, there can be a spontaneous fission reaction, which is just spontaneously the isotope will start to decay and go through this process. You could also cause really fission to occur by shooting a particle at something like a neutron and bombarding it with a neutron, which is going to create it to become unstable and cause this fission reaction to occur. So it can occur spontaneously, and it can be sort of caused by shooting particles at it. But the common sort of fission reaction usually involves, when you have a fission reaction, you get 2 new isotopes, you get some neutrons, and you usually will get energy. Now, in terms of the new elements made or isotopes that are made, you don't always get the same 2 that come out. So you don't always get the same 2 to come out. They are different a lot of times, but there are some that will commonly come out, but you might not always get the same 2 guys that come out. Here's a table, what we just talked about there. All right, so why don't you try this one? Write the nuclear equation for the positron emission of potassium. Okay, so let's take a look. We'll start with potassium, and that is 40, which is the mass number. Once again, we could go to periodic table, and if we go to periodic table, we will find potassium has a 19 above it, which means that is our atomic number. This is going to go through positron emission. So emission means that that particle will be on the product side. And for a positron, you can use the beta symbol if you wanted to. You could also have used the electron symbol, whichever way you want. So we're going to look at our atomic number here to figure it out. We got 19 on the left, 1 on the right. That means that our missing atomic number is 18. We once again would go to the periodic table, find 18, and it will say argon underneath it. our missing mass number. We got 40 on the left, 0 on the right, which means we should have 40 there on the right. Yeah. Any questions on that one there? No. So again, this is a balanced nuclear equation, mass number on the left, atomic number on the right. They both match each other. Why don't you try a few more then? Let's see here. Here we have alpha emission of uranium-238. So we'll start with 238, which is our mass number. We go to periodic table and we see a 92 above uranium. Alpha emission means that our alpha particles should end up on the product side. Again, you can use the alpha symbol or the helium symbols, okay? We will go for our atomic number. I got 92 on the left, 2 on the right. That means that my missing atomic number is 90. And I'll go to the periodic table and find number 90. There is TH. For our mass number 238 and 4 gives us a 234 in this case. Any questions on that one there? All right, beta emission of neon 24. So a little neon 24. Periodic table, we see neon's number 10. Again, emission means on our product side, and that is a beta particle. Remember that this is -1, which means I do need to go to 11 to get to 10. 11 and -1 is 10 on both sides. And 11 is sodium. Up on top, I have 24 and 0, which means I will have 24 left over in this particular case. Any question on those two there? Coming down to our nitrogen, which is 13, mass number, atomic number from the periodic table there, number 7. Again, emission here, positron, which is our positive electron. You could also use the E symbol for both of those instead of the beta symbol. We will then go one less here. So that's going to be 6, and that is going to be carbon. And up on top would be 13 in that case there. Lastly here, beryllium 7. Beryllium is number 4 on the periodic table. Electron capture means that the electron is actually on the reactant side as it's being captured or added to it. And that electron is a 1, 0, -1. There we go. 0, -1. That means that 4 and -1 means 3 is our missing atomic number. And that should be lithium. And up on top should be 7 in this case. Any questions on any of those equations? So balanced nuclear equation is not too bad, just a little bit of adding and a periodic table. Our entire final should just be these. Just add them together. Any questions on how to balance nuclear equations? All right, then let's take a look at some other things. As I mentioned before, we talked a little bit about, or we will talk about in this class, stability. And there's different ways that you could look at stability of nuclides. And one common way is the N to Z ratio. That is basically our neutron to proton ratio. And there is a certain ratio that is sort of acceptable or considered stable. Now, if you are sort of outside of this ratio, you may be a little too high, which means your N to Z ratio is too high. We need to bring down that ratio by basically converting neutrons to protons, and it will go through a beta decay. So if you find the ratio is too high, your guy will go through a beta decay, and it will move it closer to it being more stable. It may not make it perfectly stable, but it should move in the right direction towards being more stable. Now, the opposite is true. You could have a ratio that's too low, and in that case, we actually convert protons to neutrons, and that will bring the ratio up a little bit to this more stable ratio. And that is done through either a positron emission or an electron capture. could also do an alpha decay, but that's not very efficient. So for this situation, we will stick to these two. We'll stick to either a positron emission or an electron capture. Now, you may be saying those seem like two different things, and they are, but if we were to look, for example, at the one that we just did, which was down here, this was an electron capture. If we started with the same thing here and did not an electron capture, but did a positron emission, we would end up with 3, 7, and lithium. You will end up with the same thing. So if you do a positron emission or an electron capture, the resulting sort of nuclide that you make will be the same. So that's why you sort of have that option on that one that you kind of do either one. They both will give you the same result in that particular case. So how do we know if really our ratio is too high or too low? There is what is sometimes referred to as the valley of stability. Some belts call it the belt of stability. It is sort of this ratio here. And that what we're talking about again is if we're too high, we're going to bring it down with a beta decay. If we're too low, we're going to try to bring it up with a positron emission or electron capture. So the breakdown is this pretty much. If you're somewhere between 1 and 20 in terms of your atomic number, an acceptable ratio is 1. As you go from 20 to 40, the acceptable ratio is 1.25. As you go from 40 to 80, the acceptable ratio is 1.5. Anything above basically 84 is not going to be stable. It's going to be radioactive. So here's the deal with this. There is definitely some gray areas. And what I mean by that is you can see the first one goes from 1 to 20 in terms of the atomic number. And then the next one is 20 to 40. And the next one is 40 to 80. So there's sort of a gray area between where one sort of ratio cuts off and the next one starts. So for us, we're just going to do it. These are going to be hard cutoffs. So either it is that number or it's too high or too low. So we'll just use these as just really hard cutoffs. In the book and stuff like that, they may find some grayish areas in that 20-ish range. Well, it's okay because it kind of falls on the next one. It's not too bad in terms of stability and stuff like that. So for us in here, we're just going to use these as hard cutoffs. Either it is that number or it's too high or too low. Any questions on that there? So let's take a look at magnesium 22. What's going to happen with magnesium 22? What kind of radioactive decay? So the first thing we want to figure out is really what is the ratio? So magnesium 22, if we go to the periodic table and we find magnesium is 12, that means that is our atomic number. That means here the number of protons is going to be 12, which is our Z basically, right? The number of neutrons is going to be 22 minus 12, which is 10 in this case. And we're looking at our N to Z ratio. So we would take 10 divided by 12 in this case. And this will give us a ratio here of 10 divided by 12, 0.833. Now, because this has an atomic number of 12, it falls through the 1 to 20 range, which means the acceptable or stable ratio is 1. So in comparison, it is too low. So we're like down here, we need to bring it up. Remember that when it is too low, it will go through either an electron capture or a positron emission. So if we were to write our equation of what's going to happen, we would take our 2212 magnesium, do an electron capture. That's going to give us an 11, 22, and 11 is sodium. Or you could have done 2212 magnesium, a little positron emission, sodium. Either way, you will end up with sodium 22. Now, if we look at sodium 22, did we get better? Well, let's see. So the number of protons in this guy is 11. Number of neutrons is 22 minus 11, which is 11. That means my N to Z ratio here is 11 divided by 11, which is 1. So that actually moved us right onto the belt of stability by allowing this to go through this decay process. First off, any question on any of the calculation there? Will this always happen? The answer is no. You won't hit a perfect ratio after one sort of decay process. You don't have to, in these type of problems, keep going until you hit something that's stable. You just need to show the first sort of decay process that it should go under. What you should see is it should definitely move in the correct direction. So since we were too low, you should see your new guy have a much higher ratio than where you started, and at least moving in that right direction. Any questions on that there? All right, why don't you try the next one then yourself? Krypton 85, is it stable? And if it's not, what type of radioactive decay, write the equation, will it go under? And krypton is 36 for those at home. Okay, so let's take a look. Once again, we're going to try to figure out our ratio here. So we have krypton, got 85 and 36 from the periodic table. Number of protons going to be 36. Our number of neutrons would be our mass number minus our atomic number. So that's an 85 minus 36. It's a 49. So our N to Z ratio would be 49 divided by 36. Going to give us a 1.36. This is an atomic number between basically 20 and 40, with the acceptable ratio 1.25 in this case. And in this case, that means that we are too high here. And because we're too high, it will go through a beta decay to try to fix it. And if it does, we will have 8536 krypton, going to give off the beta particle. That means we're going to end up at 37 and 85, 37 being RB in this case. So if we look at where we ended up, that means the number of protons is 37. Our neutrons are now 48, I believe. Number of neutrons, 85 minus 37, 48. Our N to Z ratio would be 4837. Get about a 1.30. So not a perfect ratio, but definitely starting to bring us back down from where we started at 1.36. This again is moving us closer to sort of our stability. Any questions on that there? So neutron to proton ratio, a good way of looking at stability. And obviously you should be able to calculate that there. Now, in addition to the N to Z ratio, there are other things that we look at in terms of stability. We can look at the numbers of protons and neutrons. And as you can see on the table on the bottom, pretty much the best arrangement is when everybody's even. So if you have even protons, even neutrons, there's 157 nuclides that are stable in that sort of arrangement. The next sort of best thing is even protons, odd neutrons. There's about 53. Odd protons, even neutrons, 50 of them. The worst situation in terms of really stability here, in terms of our nuclides, is if you end up with an odd number of protons and an odd number of neutrons. You can see there's only 5 that's sort of stable in that situation. So that's also a very common way. Sometimes people are just quickly thinking about sort of stability. Do you have kind of even protons and neutrons, or odd and odd, which would be not so stable in that sort of situation? Also, if the number of nucleons, and nucleons is something that's used a lot in nuclear chemistry, it basically means the particles in the nucleus. So really what we're talking about there in most cases is protons and neutrons, really like the mass numbers, sort of what we're talking about there. And if the total number of nucleons adds up to a magic number, the nucleus is stable. It's kind of like things adding up to like electron configuration or noble gas configuration, which is really, really stable. We also find that most are stable when either the neutrons or the protons have these numbers of 2, 8, 20, 28, 50, 82, and your mega number of 126 there, number of neutrons. So those are kind of stable sort of arrangements of protons and neutrons. Any questions on that there? All right, we're going to lay it up there for today.